Okay, let's start today's seminar. Today's speaker is Biswajit Karmakar from University of Silesia. He'll talk about the phenomenology of discrete flavor symmetries beyond the neutrino masses and mixing. We start when you're ready.
Yeah, thank you for the introduction, and thank you for having me and the opportunity to make this talk here today. As the title says, I will basically talk about some phenomenological aspects of discrete flavor symmetry, like non-Abelian discrete flavor symmetries. To be specific. Now, before going into that, so this is the outline of my talk. So basically, I will first introduce the neutrino parameters appearing in neutrino physics and why we need some additional symmetry and what are their general frameworks and what implications they may have in particle physics and cosmology. And in the end, I will talk about some recent developments and then I will mention how to falsify this kind of model. So we all know that neutrinos have masses and they mix. And this mixing can be parameterized in terms of this mixing matrix, which is basically a combination of three Euler rotation, which involves three mixing angles and one symmetries, which is called the Dirac symmetries. And in addition to that, if neutrinos are not in a particle, there will be two more phases. And the magnitude of this matrix is something like this, which is quite different from the quark sector. And in this talk, we will concentrate mainly on this lepton mixing matrix. Now, this is what we know about the lepton masses and mixing. And you can see that the neutrino masses are very light compared to the other standard model fermions. And if there are three active neutrinos, it can have we can have three non-zero neutrino masses, which can basically lead to, we can construct two mass square differences out of these three mass square differences. And experimentally, we already know this properly, the solar mass square difference, which is positive, but we still do not know what is the sign of this atmospheric mass square difference. This basically gives two different possibilities, where in one case, the third mass eigenstate is considered to live here. That is called normal ordering. In other case, the third mass eigenstate can be the lighter one, which leads to basically the inverted ordering. So this ordering is also unknown. Now, for neutrino mixing, we all know that starting from the era of SNO or experiments of that generation, we have traveled a lot. You can see that the measurement of neutrino oscillation parameters have improved a lot, but not all of them. Still, there is some ambiguity over the Dirac phase and also on this guy, this atmospheric mixing angle. So it can be something between 40 to 50. So that means it can be either greater than 45 degree and it can be less than 45 degree. And that basically changes the flavor modelability, which I am going to talk about. So you can see that these two mixing angles, theta 1, 2 and theta 2, 3, they are basically well established for a long period of time, over almost 2 decades. And this third mixing angle, which is the reactor mixing angle, this has been measured in a comparatively recent times in the same year of Higgs discovery, and it is found to be around 10 dB. This is small compared to this two mixing angle, but it is sufficiently large compared to what people used to thought. And that basically has led to a different game at all in this flavor model building, which I will mention in a moment. So to understand all this, we need something beyond standard model. And in this talk, we are
Why the 3 sigma range of delta CP can go above 360?
okay, so I guess they have summarized in a consistent manner the value which are greater than 360 degrees is basically 0 to that. Okay, so basically we need something, some theory to understand these oscillation parameters. Now, in summary, this is the present status from 3 different global analysis group, and they basically kind of predict the same values. Now, as I have mentioned, few years ago, this was not the case, and like around 10 years ago, when theta 1,3 was considered to be 0, and if you consider this guy theta 2,3 to be exactly 45 degree, which is still true today, you can have a simple mixing matrix from the standard neutrino mixing matrix. Then you can see that this matrix is only function of this theta 1, 2. Now, if you choose different values of this theta 1, 2, you can simply lead to different configuration of this matrix. So if you take theta 1, 2 also to be 45 degree, then it is called bimaximal mixing, and and then if you take theta 1, 2 to be this value, then this mixing matrix is called tri-bimaximal mixing, and similarly other possibles are also there. People have also tried to connect neutrino mixing with golden ratio mixing and even hexagonal mixing where theta 1, 2 is 30 degree. So what is the advantage of having such simplified form of the UPMNS mixing? So with this kind of mixing matrix, let's say example of this one, this tri-bimaximal mixing. Now with that, you can simply diagonalize a neutrino mass matrix of this texture. So this special configuration is called mu tau permutation symmetry. In this case, the Lagrangian is invariant under mu tau permutation symmetry. That means if you change the flavors of mu and taus, the mass matrix basically will remain invariant. And in that case, what you get is that you exactly get the tri-bimaximal mixing from this. From the previous mass matrix. But we know that this is not the case. This tri-bimaximal mixing is presently not the case. So we need some deviation here. So what symmetry can play this role? Now, to address this issue, there are several approaches. The first one is called anarchy. Now, in anarchy approach, everything is random. People say that there is no such guiding principle to obtain the equal coupling. Instead of nature have just chosen some values, and in that case, everything is random. There is no as such prior correlation among the neutrino mixings. Now, the next is texture analysis, where people consider some special texture of the neutrino mass matrix, where for simplified cases some zeros may appear, but still it is not originated from any underlying symmetry. And the third approach, which is symmetry-based approach, on which the talk will deal with, where we incorporate some guiding symmetry for the Lagrangian, and that symmetry basically lead to non-trivial mixing in lepton sector. In some cases, it can also be included for quark sector.
In anarchy, how do you explain the mixing stuff?
So what I understand, they just use some like random analysis. So they have some definition of the probabilistic definition of the hep-ph mixing matrix, and from random draw, they try to reproduce the exact numbers. So, the works by whoever.
I don't know how it works, but it seems like just we have two large mixing zones for mixing. So Anarchy doesn't affect this.
But initially they proposed this idea with theta 1 c 0, and like few years back they have also incorporated with theta 1 c also. Yeah. So
Can you go back?
yeah, sure.
The other slide. Go back. No. Yeah. So probably I don't know this. That's why I'm asking. So you just assume mute symmetry, and then it will automatically give you this mass matrix, right?
Yes.
And then you need to diagonalize this. If you diagonalize, then you will get the PMS matrix.
Yes.
But
Yes.
that should also depend on the nuclear mass, right? Light nuclear mass. And if let's say light nuclear mass is 0, the lightest nuclear mass is 0, then again you will get this PMS matrix or not?
So let's say your one of the lighting mass is 0, like, because you need at least 2 non-zero mass cycle state, and in that case also this neutron or matrix.
So in that sense, it's independent of the light mass or not? I mean, if you consider non-zero, let's say mass, all of them non-zero.
Yeah, it is independent of that. Like, so you can
That
have
comes from diagonal.
yeah. So basically, so this is a general form of mu tau symmetry. So you can have some special cases, or so like it depends on the nuisance of the model building. So how you can make one neutron mass 0. Okay, so why we are interested in incorporating such clever symmetry? Because you know that these symmetries can also give some idea why we have like 3 generations of fermions and the mass hierarchy underlying them. And this clever symmetry can also be like many types, starting from continuous groups to discrete groups. And there are a few examples here, which I will talk more about. Now, for the continuous group, you know that if we take example of order-dimension models, so this kind of symmetry, it can also lead, like it can only lead to some hierarchical structure of the Yukawa coupling, not the full flavor structure for the Yukawa couplings involved in the lepton sector. Now, the cutoff scale in this theory can be linked with some BSM phenomena starting from dark matter to radiogenesis, etc., etc. So, in summary, these non-Abelian discrete symmetries are a very good candidate to understand non-trivial mixing in the neutrino sector. So here, sorry, I have listed a few groups which have like the 3-dimensional representation, and having 3-dimensional representation in the theory, particularly in this kind of theory, is very good because they basically unify the 3 generations of leptons. Now, the general model building approach is this. So you start with some bigger groups, and it can lead to different residual symmetry for charge lepton sector and neutrino sector, where these STU, not to be confused with the STU parameter, these are just the generators of this group. And if there is some residual symmetry, it can lead to some additional correlation among the neutrino mixing. So typically, for example, this kind of residual symmetry sometimes considered to be exist in this kind of model building. Now here is an example. So this is example for S4 symmetry. Now we know that S4 is basically a permutation group of 4 objects, and its generators satisfy this relation, and the three-dimensional representation, irreducible representation can be written in this form. Now, with this, if your charge electron mass matrix is invariant under this transformation, and the neutrino mass matrix is invariant under this transformation, and if they satisfy this relation, then from this kind of generators, we can simply obtain the diagonalizing matrix for the neutrino sector, and this basically gives the tri-bimaximal mixing. People have also showed that for different configuration, the other fixed mixing schemes can also be realized in the context of various discrete groups. But we know that this θ13 is non-zero. Therefore, all these fixed mixing schemes are basically absolute. So we need to like either throw them away, or we need to make some modification or correction, or find some alternative of this mixing scheme, so that we can explain everything in this table. So the first thing is this tri-bimaximal mixing and descendant of that mixing scheme, because if you apart from this θ13 0, the other two mixing angle are already still are in the correct ballpark. They are basically compatible with correct data. So if we consider that this mixing scheme is the first order approximation of the observed data, then we can say that there is we need some correction to this to have like appropriate neutrino mixing, and people have done that. So if you preserve the first column of this tri-bimaximal mixing, it is called basically TM1 mixing, and if you preserve the second column, it is called TM2 mixing, and obviously you need something in the third column. And in that case, these two are basically the mixing matrix for neutrino. This is the full TM1 and TM2 mixing. Now, if you compare the correlation among the parameters appearing in this TM1 and TM2 mixing, what we find in the context of present data is this. So this is basically the correlation among this θ23 and delta Cp. In the context of present data, this band is due to the uncertainty in the other two parameters, and this is the allowed data. This is new fit 5.2, and you can see that present data already rule out some part of this correlation between these two oscillation parameters. And here I mentioned these two parameters because the ambiguities are there in these two parameters, because we still do not know whether it is greater than 0.5 or less than 0.5, or what is the exact value of this delta. So this is basically present status of this TM1 and TM2 mixing. Now, apart from neutrino mixing, what we still do not know is the nature of neutrino mass, whether they are Dirac particle or Majorana particle. And but what we know is the bound on absolute neutrino mass and the effective mass parameter appearing in the neutrino reduced double beta decay. And there is some cosmological bound on this mass of these neutrinos. So, and this kind of Leber models can be constant from these kind of neutrino reduced double beta decay or absolute neutrino masses. But what we know about that, we need obviously non-zero neutrino mass. We do not know whether they are Dirac or Majorana. But here, let's say for Majorana neutrinos, from the Weinberg operators, we can have several seesaw scenarios, and we can also have this kind of radiative neutrino mass. And in recent times, people have also proposed some hybrid scenarios where this seesaw and radiative neutrino mass, like they can combine together. Sanjay has also worked in such scenarios. Now, first, I'll give one example where this neutrino mass and the dark matter is connected in a particular flavor symmetric model. So the model starts with A4 discrete flavor symmetry with and this A4 symmetry is basically event permutation of 4 objects. It is subgroup of the S4 group, which I just mentioned, and it also has three-dimensional representation. Basically, this is the smallest group which have three-dimensional irreducible representation, and we will assign the lepton doublets to the three lepton doublets to be triplet of this group. Now, with this group, the type 1 seesaw basically reproduce tribimaximal mixing in this model, and then we have this additional scotogenic contribution, which basically creates a deviation from this tribimaximal mixing, and having this scotogenic contribution is good because it can also lead to some potential dark matter candidates. So, as a whole, this model, this flavor symmetric model is very predictive because it can give rise to the observed neutrino mixing scheme and also predicts some absolute neutrino mass parameters and constants for LFP decay. So let's see what we are having in this model. So this is the flavor structure of this model. You can see the type 1 seesaw contribution is written in this fashion. So here we have some additional scalar field which are singlet under standard model symmetry, but they are triplet under A4 symmetry. So if you have, if you write your Yukawa coupling in this way, then you can see that this H and N, they are singlet under A4, but this L and phi S, they are triplet under A4. So if you have that, so basically, if you have this, let's say you are writing this lepton. So you have this one, and so this phi S triplet, it can be written as phi S1, phi S2, and phi S3. And if you follow the A4 multiplication rule, which is given here, because we need to have a singlet from this multiplication, and then what we will have is this L1 phi S1 plus L2 phi S3 plus L3 phi S2. And if we consider some specific potential for this phi, wave like this, let's say this is this one. Yeah. So then, what we will have is this. This will be 0, and this will be minus Bs into plus Bs into. So basically, from here you can obtain the first column of the Dirac-Yukawa coupling. Similarly, if we consider the second term, you will have the second column of the Dirac mass matrix. And obviously, the right-handed neutrino mass matrix will be diagonal in this case. Now, with this, we can write the type 1 contribution.
Sorry.
Yeah.
So in this case, the last two terms in the so-called line, so they are the usual so type 1 seesaw mechanism, right?
Yeah, this one.
Yeah.
Yeah.
So in this case, what is the advantage of considering A4?
Yeah, so the advantage of having A4 is that you can have this kind of special structure of the Yukawa coupling. Yeah, the Dirac mass matrix. Otherwise, you do not have any control. Like either you have to assume some entries to be 0 by hand, or
Okay, so you are saying that we cannot write down the three the usual Yukawa term as
Yeah,
in the standard.
exactly. So due to
So-
this symmetry, yeah.
Okay.
Yeah, exactly. So that is why we have written in this way, because the symmetry basically forbids the tree level Yukawa coupling. Because
And do you think the scale lambda, capital lambda, and n,
Yeah.
the right handed, do you think they are the same order?
yeah, so there can be, so for type for pure type 1 seesaw scenario, they are more or less same. Obviously, lambda is slightly higher than that.
What is the reason for 2 5 with 2 5 days and 5 days?
Yeah, so this is basically like, so if you consider the same phi s and phi a here, the mass matrix which you will have here, it will be incompatible with the data. So to have a like observable neutrino mixing, we have considered this. Okay, so similar way, the scotogenic contribution can be written, and effectively, this is the neutrino mass matrix where both type 1 seesaw and this one loop scotogenic contribution uh, contributes. So now, if you rotate this mass matrix with the tribimaximal mixing matrix shown earlier, you can see there are still some off diagonal entries. So you need some additional rotation. And that additional rotation basically give rise to the TM2 mixing in this particular scenario, which will obviously lead to like correct theta 1,3, and this is the correlation among the oscillation parameters in this model. So in this clever symmetric model, the advantage is that they are very much predicted. You can see this is the correlation between delta Cp and sin square theta 2,3, and this part is disallowed. And this is the prediction for neutronless double beta decay, and you can see that the prediction for inverted hierarchy, this is already kind of it will be basically proved by near future experiments. So then this part will be gone. So and it can also lead to see at some part of the normal hierarchy scenario. And also there will be some constant from the neutronless double beta decay. And since there is clever symmetry, there will be some decay modes will be on and some decay modes will be on. So I'm not going into the details of that. But having this photogenic contribution basically leads to various dark matter, potential dark matter candidates. It can have the scalar dark matter scenario. It can have a fermionic dark matter scenario. So in this case, what we see that for the dark matter to be, so this basically this plot is a little bit, we have updated it because this is not the correct one. So to be in this particular model, to be consistent with the LFB constant, the dark matter, what we find is that it is somewhere around 1750 or so. So the dark matter can also be realized in this case. So theta 1,3, which is generated from this photogenic contribution solely, it can also lead to potential dark matter candidates. Now, what? Yeah.
This photogenic matter. In terms of like lambda square coupling.
Yes.
So effectively the coupling is not.
Yes.
How can this certain dark matter be thermalized?
So in this case, what we
Theta is a gauge, double it.
yes.
And in case of fermion,
Sorry.
in case of F, like fermionic dark matter.
Yeah.
If F have other interactions?
No. So for example, what you have this in this case is effective Yukawa coupling. So this is ys lambda square, phi s, and the wave of these guys. So that will, this whole thing will be constant from the dark matter analysis.
This is order 1 like
Yeah. So yeah, something like that.
So they are asking that the NA
Yeah.
is diagonal in your analysis.
Yeah, exactly. So you can see that. Sorry. So these are basically singlet under the A4. So this is just like and there is one such guy. So it's just a bare master for that.
Yeah, because I just wonder how many parameters are left.
Yeah.
By
So yeah, so you can see that this mass matrix can be written in this form, this A, B, and C. And this A, B, and C, they are basically, so this C is coming from this scotogenic contribution. So obviously you cannot constrain the each individual couplings from the neutrino mixing alone. Okay, neutrino mixing will only constant the ratio of these guys, which is appearing here. So I have not explicitly mentioned the expression for the masses, but you can see from this mixing analysis, we can constant this alpha. So this alpha is basically ratio of these two contribution from the scotogenic and seesaw, and this phi AC is basically the phase. So we can constant these things from the neutrino oscillation. Also, there will be some constant from the neutrino oscillation data, and that I have not given because these are more realistic ones. Yeah, so anything else? Yeah. Now, apart from these descendants of tribimaximal mixing, I will now talk about some other scenarios which are still feasible. And one such is this co-bimaximal mixing. Now, what is that? Now we know what is mu tau permutation symmetry. That means the exchange of mu and tau flavor. Now, if we also introduce the CP symmetry with that, that is called the co-bimaximal mixing. And in that case, the neutrino mixing matrix will satisfy this kind of modulus relationship. And you can write this mixing matrix in this way. And the mixing matrix which is diagonalized, that can be written in this form. You can see the difference. So in the earlier case, this B and B, they were same. Now this is basically B and B star. So this is the difference. Now, this basically, introduces non-zero theta 1, 3. And this is a simple model building with that, which will come soon. So I'm not just going to that, but this co-bimaximal mixing, what it does is it basically reproduces theta 2, 3 to be exactly 45 degree, which is still valid, and this delta CP to be exactly minus 90 degree, which is somehow in the correct ballpark of the experimental observation. But in case in future, suppose this is not the true, then possibly we need to throw away this model, this co-bimaximal mixing, or we need to come up with like similar way some modification to the tribimaximal mixing. Something need to be done. And what people do is that this kind of symmetry is called this co-bimaximal mixing is sometimes also called mu tau reflection symmetry. Now, similarly, if we imply this mu tau reflection symmetry in the one of the column of the neutrino mixing matrix, then that will also lead to some correlation between these two mixing parameters. And you can see, just like the tridimensional TM1 mixing or TM2 mixing, some part of mixing for this partial mu tau symmetry, it can also be ruled out. Same thing can be exercised if you introduce additional neutrino state also. Yeah. So now, so far we have talked about some smaller groups. Instead of that, people have also tried to address the issue of understanding of neutrino mixing, starting from a very big group. The problem of this group is that everything is like the breaking pattern and the wave alignment of these groups is very much complex. So people have done it numerically. So if you demand also some residual symmetry, people have find that the smallest group which can lead to correct neutrino mixing is this coming from these series groups, delta 6 and squared, and where n is 80, which can lead to correct neutrino mixing. Now I will talk about some implications of flavor symmetry in like cosmology. So first thing is leptogenesis. We know that if we have right-handed neutrino or other heavy particles to explain light neutrino mass, then from the out of equilibrium decay of that particle can lead to electron asymmetry in the Pauli universe. So this is the example with type 1 seesaw where the right-handed neutrino decays. And this is the expression for the CP asymmetry parameter, which appears in the Boltzmann equation. And solving that, we obtain the final baryon asymmetry. You can see that this asymmetry parameter is basically function of this Yukawa matrix, and which basically dictated by the flavor symmetry. And so therefore, the flavor symmetry will also have some implication on this kind of Leptogenesis scenario. So all the so if you have something, some flavor models, then it will obviously lead to some correlation or some constant on the lepton if you have some leptogenesis mechanism there. So for example, this alternative equilibrium model which explain tribimaximal mixing, those class of model, the structure of Yukawa coupling is such that it lead to the y dagger y to be unique. Therefore, then you will not get any imaginary component out of that to have non-zero symmetry parameter. So basically, this will be epsilon zero. So this tribimaximal mixing, this is not only ruled out from neutrino, from neutrino oscillation data observation, like it is not, it is in conflict with θ13. It is also in conflict with the observed lepton asymmetry of the universe. So if you want to incorporate lepton asymmetry, this is not sufficient. So this is also one way to look at it, that we need something beyond tribimaximal mixing. So obviously we can do something by incorporating some like higher dimensional operator, which basically deviates the leading order Yukawa coupling, and that will basically lead to the non-zero entries, the required non-zero entries, which basically will lead to observed baryon asymmetry. So this is one such example. And also we can, so this is the example with this co-bimaximal mixing. Leptogenesis can also be realized there. Okay, so dark matter part I have mentioned, I will not go here. But one thing which I want to mention is that this kind of flavor symmetry, it is very hard to prove in the collider at least. But in this work, these authors have studied this series group delta 6n square, which also have CP with that. So delta 6n square with CP. Now, what happens is that this group basically breaks down to some residual groups, and this theta r is basically related with the residual groups. Now, if you try to enhance this residual symmetry, then they have find that some of the heavy neutrino state, they decay late. So you can see that for specific values of this when the residual symmetry is enhanced, there is a chance to detect these right-handed neutrinos when there are a few hundred GeVs. But there are some drawbacks which I must say about this flavor symmetry, and there one is that we do not know what is the origin of such discrete flavor symmetry. So if everyone proposes one discrete flavor symmetric model, so it is basically completely random. And other thing is that the particle content is not minimal. Sometimes there are many scalars involved to realize the flavor structure of the required mass matrices. And not only that, also you need some kind of auxiliary symmetries to have like your desired mass matrix. Like for the example which I showed, that some auxiliary symmetry basically forbids the tree-level Yukawa coupling. That's why we have the next to leading order contribution. So in a nutshell, it's not very much minimal. And apart from that, the flavons which are involved in this analysis, the vacuum alignment of those A4 flavors is not very much trivial. So there are many ways to do it, but people have done it, but it's not very trivial. So in a nutshell, so there are some drawbacks of this model. Now, to address these drawbacks, recently people have proposed a new idea, which is called the modular invariance approach. Now, where people consider that the neutrino mass, it can be written from the modular invariance approach in the lepton sector. What basically done is that you do not need these additional flavons in this case. but instead of one modular field, and that basically this complex modular field will be it will help to write down all the Yukawa couplings, and that complex parameter can be fitted with the observation or observed neutrino data. So this has just started like 5-6 years ago. Now there are many things to do in this kind of models. Now the last thing which I will talk about is that how to falsify these kind of flavor models. So there are, obviously we have to look at the neutrino experiments, and two such things is this neutrino oscillation experiment or neutrinoless double beta decay experiment. So let's first talk about how we can falsify these classes of model from neutrino oscillation experiment. So what we have discussed is that if you consider some flavor symmetry GA, and if you demand that it is having some residual symmetry, then you can write down some correlations among these neutrino oscillation parameters, which I have shown with one example. Now, if you study this correlation in the context of various neutrino oscillation or other experiments, then you can have some prediction. So these are the models which these authors have studied. So here these A5, S4, these groups are considered in with CP, and they find that the best fit value and the prediction for their cases basically are not compatible with each other. You can see in each cases the best fit value basically lies away from what the model is predicted. So these classes of model are basically ruled out from simple analysis of these proposed experiments. But the other classes of model, these kind of classes of model, simply, they are basically, you can see the best fit value lies within the allowed region. So this is one way to falsify these kind of flavor models. Now, and another way is the double beta decay experiments. So we know that if neutrinos are minor particle, then we can have some signals for this neutrinoless double beta decay. Obviously, we know that neutrinos are minor, but still we can have null signal. But still, if we are hopeful enough, let's say we will have something, we will find something, then this neutrinoless double beta decay also can falsify some models. So here, this is a very new paper where people have studied the models with generalized symmetry and their prediction for the neutrinoless double beta decay. So with the improvement of the experimental result, some models will be discarded. Now, one interesting thing is how we can falsify this flavor model based on the sum rules which these models predict. So this is, so each flavor model will produce some kind of sum rules, and sometimes these sum rules can be written in a very compact manner, and sometimes, so this is a very generalized sum rule, and these are few examples where the simplified form of this one has been realized. Obviously, there will be some model which basically do not satisfy this exact sum rules. Maybe some like approximated sum rule they can obey, but nevertheless, if any model predicts this kind of exact sum rules, they can also be studied in the context of the neutrinoless double beta decay, because this sum rule will have some definite prediction for the neutrinoless double beta decay. So you can see, so this is the update from 2013, and in that time, the sum of the model, and this is the disallowed region for the prediction. So we can see that the models which make prediction on the neutrinoless double beta decay, not many of them are basically disallowed, but this plot has been updated this year, and you can see that some guys are already ruled out just from the neutrinoless double beta decay. And one example is this. You can see that this sum rule is basically now one, at least for the neutrinoless double beta decay case. So basically, and the model and the model which basically discrete groups which consider with this A4, S4, A5, and but this doesn't mean that this A4 group is absolute. This means that this particular model is invalid. So at least we can have some way to falsify these kind of models. So in summary, what we know is that we have non-trivial mixing in the case of lepton sector, and we do not know why the mixing is such and why there are 3 generations of the leptons. Discrete favor symmetry is one such potential candidate which can explain these non-trivial neutrino masses and mixing, but we still do not know what is the origin of subsymmetry, like how they exactly play their role in other aspects in particle physics and cosmology. And the last thing is that if this kind of symmetry is not the case, then we need to look for the possible symmetry what can lead to this kind of mixing. So thank you.
Thank you very much for the nice talk. Any question?
Can you really say that you can falsify flavor symmetries? Like, for example, before we know theta 1,3 was non-zero, there were several flavor models that predicted it to be zero, right? Yes. Then it was found to be non-zero, but the models were not really falsified or corrected.
Yes.
So if you try to falsify some of the flavor models with some other measurement, can you do the same?
Yeah, so you are right. So when this tribimaximal mixing was very popular and people tried to reproduce it with this discrete symmetry, and the moment theta 1,3 was discovered, those models were basically ruled out. But people have came up with some twist in those models so that these groups like this symmetry is not basically falsified. What you can do is that you can falsify that particular model. But in the context of the neutrino oscillation experiment, where which I have shown, there you can falsify this class of model.
I think in some sense you can falsify the prediction, right?
Yes, exactly. That is the thing.
So as long as you have as many predictions as possible, you need to
So now people are like very active how to falsify this kind of, because there are enough models, so we need to falsify.
If possible, so can you explain how to get so this kind of discrete symmetries in string series?
Yeah, so this modular symmetry which I was talking about, this basically comes from like superstring theory, from compactification in one dimension. So
for example, let's consider 3 blends.
let's consider.
3 blends.
Yeah.
And we can consider a lot of excitation for the 3 blends. And the spectrum, so on this 3 blend depends on the compactification of other dimensions. And I'm not sure we can realize this kind of discrete symmetries. So by such compactification, just I don't know.
Yes, I'm also not very much expert on that string theory, but from this modular symmetry point of view, that this after compactification, the whatever Yukawa coupling you have, it can satisfy this modular group, like for example A4 or A4.
Yeah,
You can do that.
Of course, if we assume some specific compactification, so the Yukawa coupling is determined by the volume over some. So by a bond for such compacted dimension. So so that's why so many people have studied such kind of compactification. So one of the biggest problem is that so there is no reason to believe. So one with such complication, right?
Yeah, so it is basically same kind of same how you are choosing one discrete group to another. So
Thank you. You know, what do you think about blocks at all?
yeah, so so the thing is that the example which I have shown there, we have not considered quarks and also the charge density is direct. But there are models or works where people have at this quark sector, especially this modular invariance approach or this like this guard frameworks, they incorporate quark sector as well. Because this favor symmetry can also be embedded in some guard scenario. So in that case, quark sector also in.
Any other question?
Maybe it's not very right, but the sign of this atmospheric must be different. So is there an experiment which can? Experiment measure that?
Yeah, the experiment, this possibly T2K, sorry, T2HK. So they are trying to
Consider the sign of.
yeah. So the problem is that the same like different sign can do same probability. That is why we still are due to the matter effect. So that is why we still do not know the sign.
Like the hypo-K in June, they will go.
Yeah, I think I heard that in my 10 years.
Chúng ta sorry.
Very great.
The sign that basically means one of these two.
Exactly. This is a very like
Hierarchies are ruled out.
yeah ruled out, and also your double beta decay there is two band. You know,
Yeah.
one band is gone.
One hierarchy will be ruled out.
Exactly the sign. So things will be much more clear, and half of the model will be
Yeah, but out here you can see. It takes much longer than.
But I think the future limit for double beta decay is below the embedded hierarchy.
exactly. So yeah.
Next generation will touch just the bottom of the.
Yeah, exactly. So you can already determine.
Yeah, so exactly. So this NXO is below.
So like inverted hierarchy almost ruled out.
It will be.
Will
Yeah,
Yeah.
future prediction.
so these two are future.
All observed.
Okay, another question? Now let's thank speaker again. Thank you very much.